Okay, so let's now start with this new chapter whose name is surface chemistry. In this chapter, we're gonna learn some properties related to surfaces of substances. So let's begin with the theory part.
Right. So we begin with surface chemistry. In this chapter, we'll be studying some important properties related to surfaces of substances.
Okay.
Right. So we'll begin with adsorption, then we'll go on to study about colloids and then emulsions.
Okay.
So let's start with adsorption. What is adsorption? See, it's defined as the interaction of molecules at the surface to maybe the molecules can be attracted to the surface or they can be repelled, but the interaction is with the surface.
Okay.
So what
the
happens
concentration
is,
might increase or decrease at the surface.
yeah, as compared to the bulk.
Okay.
So if positive adsorption is taking place, then concentration at the surface will be greater than that in the bulk, because the molecules will come and bond with the surface.
Okay. So in positive adsorption, they accumulate at the surface.
Exactly. And in negative adsorption, the opposite of that happens.
So they are repelled by the surface.
They are repelled by the surface. So the
adsorption.
concentration in the bulk is more than that in the surface.
Okay.
Right. Now, see, there's another phenomena that we often come across, which is absorption, right? And we should not confuse between the two, because adsorption is a surface phenomena and absorption is a bulk phenomena.
Okay.
Okay. And if you see two major points of differences between them, two more major points, then one is in adsorption, unequal distribution of molecular species takes place is there in the bulk and on the surface, and while in absorption there is uniform distribution throughout. And another point is that adsorption is rapid in the beginning and it slows down as it reaches equilibrium.
So it kind of saturates.
It saturates, exactly. And absorption follows uniform rate throughout.
That's interesting.
Yeah. So moving on, we now come to two major types of adsorption.
Okay.
One is Physisorption, the second is chemisorption. In Physisorption, the molecules bond with the surface physically, like there are intermolecular van der Waals forces.
So there are no chemical bonds.
There are no chemical bonds, exactly. So since there are no chemical bonds, there is no chemical reaction taking place. Physisorption is reversible and chemisorption is irreversible.
Can you explain what's reversible?
A reversible reaction is when it can revert back to its original form if I change the conditions of temperature and pressure and stuff. Okay. The other important point.
So the molecules can be separated from the surface by changing some physical.
Exactly. Like we'll come to this. Like this is very important. The rate of Physisorption decreases as the temperature increases. Why is that so? What happens is, see, basically Physisorption is an exothermic process because molecules bond with the surface
and energy is released.
Energy is released, right. So if I increase the temperature, then by Le-Chatelier's principle, the rate of reaction will decrease because it will try to reduce the amount of energy.
Okay.
Right?
Now I got it.
Yeah. So, and in this kind of adsorption, the heat of adsorption is small.
Okay.
And equilibrium is achieved fairly quickly. Okay. In this. Now, we'll move on to chemisorption. In chemisorption, chemical bond formation at the surface takes place. That is why it is irreversible in nature. Okay. And the heat of adsorption is much larger as compared to Physisorption, and this is very important again. Rate increases as the temperature increases. Okay. And
so as we increase the temperature, chemisorption increases.
Exactly. While in Physisorption,
it was opposite.
Exactly. As we increase the temperature, the rate of adsorption decreases. And here equilibrium is achieved fairly slowly, right? Okay. And
so after a long time, saturation occurs.
Exactly. Because chemical bond formation, it has to take place, right? So it takes some time. Okay. And yeah, let's move on to the next topic. Adsorption of gases on solids depends on 6 factors. The nature of the gas which is getting adsorbed. Second is the nature of the solid on which adsorption is taking place. Third is the specific area of the solid. This is very important. That is why catalysts, we try to increase the specific area of a catalyst as much as possible.
So you're trying to say that if this area of that substance is more will be the adsorption.
Exactly.
Okay.
Exactly. And the fourth is the pressure of the solid. The fifth is the temperature, and the sixth is the activation of the solid. So now
Activation of solids means that, for example, charcoal is more activated.
exactly, because the surface properties decide the activation. Basically, there are activation decides how much tendency does the surface have for adsorption.
Yes. So
Okay.
if activation is more, the affinity for it to attract molecule is more.
Exactly. And here I would like to discuss one point. If you see an application of adsorption, a very important application of adsorption is in catalysis, right? Catalysts perform as in they operate on the principle of adsorption.
Okay, that's interesting.
Okay, so they lower the activation energy. They provide a new pathway with a lower activation energy. And how do they do that? By providing a surface for the reaction,
Okay.
on which the molecules come in and attach, and the right. Now we come to some very important concepts related to adsorption. First one is Freundlich adsorption isotherm. Now, according to this adsorption isotherm, this principle, the amount of gas adsorbed on the surface of a solid is directly proportional to the pressure of the gas above the solid.
Okay.
Okay, so as you can see this equation also, x by m is equals to kp raised to the power 1 by n,
Where
where
n is some constant that is greater than 1.
exactly.
And one thing you should remember, that these graphs are at a constant temperature. That's why they are called isotherms.
Isotherm, exactly. So as we can see from this equation, as the pressure increases,
The amount of gas absorbed.
the amount of gas adsorbed also increases,
Yes.
right? So now let's see this graph. Okay, in this graph we see that again, as the pressure increases, the amount of gas increases
Yes.
until the point of saturation pressure, at which saturation occurs and no more gas is adsorbed,
And that pressure is
even
called.
if I increase the
And
pressure.
that pressure is called saturation pressure.
That pressure is called saturation pressure. Now there's another thing. I had discussed that in Physisorption, if I increase the temperature, the rate of adsorption decreases, right? So if let's say this is at T1, this graph is at T2, right? So
So T1 will be greater than
T1 will be greater than T2, exactly.
Okay.
Okay, now I can plot the same graph in terms of logarithmic axis also. I can take log of the equation. So now log of x by m and log of p are in a linear equation, right? So I can plot that. I'll get a straight line. The slope will be 1 by n and the intercept will be log of k. This is important for solving questions, numericals directly.
Okay.
Right? So in this equation, let's see the significance of the variables. M is the mass of the adsorbent, X is the mass of the adsorbate. Now, what is adsorbent? Adsorbent is the substance on
That is
whose
getting
surface
Okay.
the adsorption is taking place.
Okay.
And adsorbate is the substance getting adsorbed.
Okay, now I get it.
Okay. And K is it's a parameter, it's a constant, and P is the pressure.
Okay.
Right. Next comes adsorption isobar.
Okay.
As we've already seen, in physical adsorption, as temperature increases, adsorption decreases.
Yes.
So we can see this curve also. As the temperature is increasing, x by m is decreasing, right?
Okay.
And in the case of chemical adsorption, as the temperature is increased, then what happens? Adsorption also
First
increases.
then it decreases.
Right, then it decreases because there is a point, obviously, there is a point to which if you increase the temperature beyond a certain limit, then the molecules will gain excess kinetic energy and
Okay.
will stop forming the bonds, right? So that way.
And also remember that it's an isobar. This graph is.
Yeah, this graph is an isobar.
So it's
Isobaric.
plotted at constant pressure.
Constant pressure, right. Now we come to another very important concept in surface chemistry called the Langmuir adsorption isotherm.
And it's an isotherm.
It's an
So temperature is
isotherm,
constant.
right? The temperature is constant. Now, there are few important assumptions in this. One is a monomolecular layer. The
Monomolecular
adsorption
layer?
takes place
Okay.
in a monomolecular layer. That means once the
So
a layer
only-
of molecules is formed, there's only one layer.
Okay.
That is the assumption. Okay. And the second assumption is that the adsorbed layer is uniform all over the adsorbent.
Okay. So the concentration is uniform at
Throughout.
all over. It's throughout. Okay.
Right. And the third assumption is that there is no interaction between adjacent adsorbed molecules. So this is a very idealized case. But then since we need to formulate a mathematical formula for this, we need to take these ideal assumptions. Right. So now if I denote theta as the fraction of surface covered by adsorbed molecules.
Okay.
Okay. Fraction is important, right?
It's a fraction.
It's a fraction, and so 1 minus theta will be the fraction of the surface which is unoccupied.
Exactly.
Or available for adsorption,
yes.
right? So now suppose I take Kd as the rate of desorption, and
can you quickly tell us that what's desorption?
Desorption is just the opposite of adsorption.
Okay.
Right? Molecules getting attached to a surface is adsorption. Molecules getting detached is desorption. Right. So Ka is the rate of adsorption.
Okay.
This should be adsorption. Okay.
Okay.
Now, so what Langmuir said was that theta,
that is the
fraction of
the
covered,
frac-
the fraction of the surface which is covered,
okay,
will be directly proportional to the pressure, and
will be given
and
by,
it will be given by this equation. Okay.
Okay.
Like you can see that as the pressure will increase, more theta will be more, that is more adsorption. As Ka will increase, there will be more adsorption. As Kd is increased, there will be less adsorption.
Because
so
it's inversely proportional.
It's inversely proportional. Exactly. So Langmuir came up with this formula. Okay. Now, if I replace Ka by Kd by a constant capital K, then I can write this equation like this.
In a much simpler form.
In a much simpler form. Now, how does all this relate to, the phenomena of adsorption and isotherm? This equation is extremely important.
Okay.
What do we get by this?
So we need to remember this equation.
Yeah.
Okay.
We need to. It's very simple. It's fairly simple once you understand the meaning, right? So,
okay,
the amount of gas adsorbed on the solid, which is given by x, is directly proportional to theta. This is theta into k.
Yes.
Right? So it is directly proportional.
So it's basically k theta.
K theta. Right. So yeah. Now this is simplification of the same equation. We obtained this.
So we have just rearranged the terms.
Exactly. So we see that this axis is pressure. So we see that there is a linear relation between P upon x by m and pressure. Right? So another important point is that Langmuir isotherm holds good for low pressure, but it fails at high pressure.
Okay.
So this should be kept in mind when we are applying this concept.
So it's applicable only for low pressure.
Exactly. Now we come to the topic adsorption from solution. So solids are capable of adsorbing solutes from the solutions also.
Okay.
In that case, if we talk about mathematical formulae, then
the same equation holds.
Exactly, the same equation holds, only the pressure is replaced by concentration here, because we're talking about a solution, obviously.
Yes.
So x by m is equals to k c raised to the power 1 by n, where the variables have their usual meaning, and c is the concentration of the solution. I can take the logarithmic form also. In that case, log x by m and log c will be plotted in a straight line, where the slope will be 1 by n and the intercept will be log k.
Okay.
But this again is valid for small range of concentration. It's a straight line for small range of concentration.
Okay.
If you take extreme values of concentration, then this might not hold true.
Okay.
Okay. Right. Now, in this case of adsorption from solution, Freundlich adsorption isotherm is also applicable, which is pretty much the same, right? We're just replacing concentration, pressure by concentration. Now we come to applications of adsorption. Now adsorption,
the interesting part.
Yeah,
okay.
It's a very important phenomena, especially at the industrial scale.
Okay.
If you see, I talked about catalysis, right?
Yes.
There are a lot of reactions which won't take place if catalysts are not provided. Let's say Haber's process. Even in Haber's process, iron is used as a catalyst, right?
Yes, so, iron and molybdenum.
Exactly. So most of the catalysts work on the phenomena of adsorption.
Yes.
They provide a surface in which the reactants attack, bond, and then
Form the product.
form the products. Exactly. Now we'll look at a few more applications of adsorption. One of them is control of humidity. So silica and aluminium gels are used to control humidity because water molecules
Get
absorb
on their
surface. Right. Now the second application is removal of coloring matter from solution. Again, there are substances, adsorption agents which you can use for this purpose.
Okay. For
Now-
example, if we had charcoal to color solution, it will become colorless after some time.
Right. But then that will happen only with certain solutions.
Okay.
Okay, this is important. Catalysts are selective in nature. So for a
Okay.
particular reaction, one substance can act as a catalyst while other cannot. So it's
Okay.
very selective in nature. This again has to be kept in mind.
So
Right.
adsorption is selective.
Yeah. And yeah, when we talk about heterogeneous catalysts, then we talk about promoters and poisons also. Basically, promoters enhance the function of a catalyst,
Okay.
and poison,
They stop the reaction.
they stop. Yeah, exactly. They affect it in a negative way.
Okay.
So in Haber's process for manufacture of ammonia, if you add molybdenum, then it acts as a promoter for iron, which is used as a catalyst.
Okay.
So yeah. Moving on to the next topic, colloids. A colloid is a heterogeneous system in which one
Okay.
substance is dispersed, and it is known as the dispersed phase, as very fine particles in another substance called the dispersion medium. Right.
Okay. So dispersed phase is dispersed in the medium, that is called dispersion medium.
Right. So these terms are important, dispersed phase and dispersion medium. We'll discuss them in detail.
Okay.
So when I talk about a solution, any solution has two phases, dispersed phase and the dispersion medium.
Okay.
The dispersion medium is continuous and it's the external medium, right? And the dispersed phase is dispersed in the dispersion medium. So
Okay.
the discontinuous phase is the dispersed phase.
So can you explain the meaning of continuous?
Like say for example, you have salt dissolved in water.
Okay.
So water is present everywhere, right?
Yes.
So that is the dispersion medium.
So it's continuous.
It's continuous, right? And salt gets dispersed in the water, right?
Which is continuous.
Yeah, and it's another case that it's a true solution. So salt is uniformly distributed, but then the continuous medium is water,
Okay.
right?
And the solution we are talking about is an homogeneous solution, but colloids are heterogeneous.
Yeah, exactly. So yeah, here I was talking about solutions in general. So now, based on the sizes of the dispersed phase and the dispersion medium, a solution can be divided into three types: true solution, suspension, or colloids. In true solution, the sizes of the dispersed phase is in the range of 1 angstrom to 10 angstrom.
So the particles that are dissolved are very small.
Very small, right? So for example, sugar or salt in solution, it's a homogeneous mixture. Then there are several properties like it cannot be separated by filtration, and it's basically very uniform, very homogeneous.
Yes.
Right? And you cannot detect the dispersed phase using naked eyes.
And
Not
Okay.
even using microscope. Like
Yes.
you need very powerful microscope for the detection.
okay.
And now we come to suspension. The size is much bigger than in case of true solution. It's around 2000 angstroms, and it's a heterogeneous mixture of solids, and the solids are sufficiently large for sedimentation.
And we can see them with the naked eye.
Yeah, we can see them with the naked eye. Say for example, sand in water is a suspension.
Yes. We
Right?
can easily see sand particles in water.
Yeah, they do not dissolve. The third is colloids. Colloids fall in between true solutions and suspensions. The size range is around 10 to 2000 angstroms.
Okay.
Right? So their properties also lie between these two solutions.
Okay.
Now we look at the classification of colloids. We look at the classification of colloids and there are different bases on which colloids can be classified. Like for example, on the basis of physical state of dispersed phase and dispersion medium. So we have gas, liquids, and solids, right?
Okay.
So there can be various combinations.
That
Like
if the medium
there can
is-
be liquid gas colloids,
Okay.
there can be gas solid colloids. But yeah, there should be 9 possible cases. But gas and gas is always soluble. So gas and gas is a true solution. So
Okay.
there are 8 types of colloids possible if you talk about this kind of classification.
Okay, so
right?
you mean to say that gas plus gas is always homogeneous?
Always homogeneous. They will always form true solutions.
Okay.
Now the second form of classification can be on the basis of interaction between dispersed phase and the dispersion medium. So on this basis there can be two kinds of colloids possible, lyophilic and lyophobic. Right, we'll discuss these in detail.
Okay.
And the third type of classification can be depending on the types of particles of dispersed phase. Okay, so it can be multimolecular, macromolecular or associated colloids.
Okay.